The fundamental theorem or theorems of calculus are really key to applying integration to solve real-world problems. And there are two of them. Historically, there's the first one and then the second one. But I think in terms of how often they're used, the second one is the more important. So let's just do a quick peek at what we're talking about here. We're going to take an integral, and I'm going to write it in a little bit of a funny way. I've got the integral over the interval from a to b of f of x dx, and I'm doing this in color on purpose because, as a reminder, there is no x there. This is the same as the integral from a to b of f of, pick any other name that you would like, not f, not a, and not b. So this is f of t dt. So this is a fundamental thing about integration. There is no x, there is no t. It's every a and b in between that goes on here. And what this integral tells us, among other things, and that's where the application part comes in, is the area. It's the signed area of under the graph of f. Well, signed might mean above the graph of f, between a and b. So there's an area here that gets counted positively, and there's an area here that gets counted negatively, and that combination of areas with the signs is the integral. So to get to the fundamental theorems, it's actually easier to understand what's going on if you take a passive function. So what I was imagining was those traffic counter things where they lay a pneumatic hose across a highway, and it counts how many cars go by, and someone goes out there once a day and says, oh, we've had so and so many cars per day on Tuesday, and so many cars per day on Wednesday, and so many on Thursday, and so forth and so on. So this is a passive function. The function is not variable. You can't do anything to it. You can't modify it in any way. And so what you get with this passive function is some kind of graph like this. It's probably pretty wickety-whack. And so I'm going to call this function c of x for cars per hour. And I started to write a variable there, but let's say we start at 6 a.m. and we end at 6 a.m. the next day. And so we get these 24 data points, and we imagine that there is an active function that goes between them. There are two things that we can do with this situation. So c is cars per hour. Wait a second. Cars per hour. C is a derivative. So c is in cars per hour. That's a rate. So c is the derivative of something. I'm going to call it n for total number. So c is a derivative, and that's important. That'll come up in one of the two fundamental theorems. Now, there are a couple of things that we can do with this graph and understanding this area. Now, in this case, c seems to be positive everywhere. So one thing that we can do, which is kind of interesting, is say we can go from 8 o'clock until 10 o'clock, and so what we're going to say is we had so and so many cars per hour all this time, and this area is going to represent the number of total cars that happen, say, during rush hour between 8 and 10. So the integral of c of t dt from 10 to 12 is the number of cars. There's another thing that we can do here that is much more interesting, and this is probably the one that gets used the most in applications because this is used in statistics. So what we're going to do is we're going to start at 6 a.m. and we're going to have the graph, and so that part should be about the same. But now we're going to look and see what happens as we change the time interval. So what we're going to see here is that the endpoint here is variable. And that enables us to do something very interesting, which is to turn the integral into a function. And so that's where the second fundamental theorem comes in. This is one of the key steps in doing any kind of statistical analysis, is this kind of thing right here. So we're going to have the integral from 6 to x of c of t dt. And so that's a function, and we're going to, well, we better give it a name, so I'm going to call it n of x. And you have to be a little careful with notation here, because what you have is x is up here, so x can't be down here. You can't have the same x with two different meanings. And so, the symbol representing all the points in the interval between a and x is t, and x is the endpoint. So a little bit of a change there. And because this is a function, well, we can take its derivative. Well, we can try to take its derivative. And so, I'm going to go through that. It's kind of an interesting situation here, because n prime of x is limit h near 0 of a big old nasty fraction, h on the bottom, and then n evaluated at x plus h minus n of x on top. Standard definition of the derivative. But now we have a geometric interpretation, because we've got the area. N of x plus h is, I'm just going to put x plus h out here. N of x plus h is the area in green. So there's x plus h, and n is the area in green. And n of x is the area that I'm doing in black, integral from 6 to x. So that's the area there. So we've got a lot of stuff that's moving around. And the top of the fraction that we take the limit of to take the derivative is, well, I'm going to color this in red. And that's the difference between the two areas. There is the bigger area minus the smaller area, assuming h is positive in this. And so that leaves us this area. And so well, when we do an integral, we normally do the 4-step subdivide, sample, sum, and sometimes take the limit. And actually, we're going to do all those here. What we've got here is we've got, I'll rewrite this lickety-split. So we still have limit for h near 0 of h over the integral from x to x plus h of c of t dt. So remember, this curve is c, and what we're ending up here, this little strip goes from x to x plus h. And we would like to estimate that integral. That integral, it's already been subdivided. H is already small, so we're going to use a subdivision with one thing. And so we're going to have a picture kind of like this, where we have x and x plus h. And we want to know the integral. And so we're going to take a sample. That's how you do integrals. We're only going to take one sample, so I'm just going to call it c sub 0. And the integral is approximately, let me write out what the integral is. It's approximately h times c sub 0. We've only got one sample, so there's the sum. The sum only has one term. And so this integral out here is represented by this picture here. Let me get it so you can see them both. And that's h times c sub 0. Well, that's the top of this fraction. And so what we're seeing here is that n prime of x is limit h near 0 of c sub 0. Yeah, the h is canceled. There was an h here, and there's an h here. They canceled. And so this is c of x. And that's the second fundamental theorem of calculus. So when you write it out, it looks kind of funky. So I'm going to try to use some colors to help us. So we're taking an integral from a to x of some function f. This is the more general thing. It's the more abstract. So I've got the x's color-coded here. So we're going to take that integral, and what we're going to find is, what we find every time, is that when we've got this function, excuse me, if you get rid of this, we have a function, and then we're taking its derivative, and we take the derivative, we get just plain old f of x. So that's the second fundamental theorem in the green box. There. That's the second fundamental theorem, and it's not so much that we use this theorem very much, but we use this technique of letting the endpoint vary is such an important technique in all the statistical things, and we'll get to those kind of toward the end of the term. And so this is the second fundamental theorem of calculus. We'll say a little bit about the first fundamental theorem. The first fundamental theorem is overemphasized. It's overemphasized because we don't really use it that much, because it requires having an active function, and active functions don't happen in actual applications. So stick to your passive functions, understand the theory of the integral. We've done the subdivision, we've done the sampling, we've done the sum. In this case, we only had one thing, and we took the derivative and found something that is extremely useful in almost all of the applications of calculus.